Hello everyone. So today's lesson is on 8.4, the law of logarithms. From some of those facts that we talk about in 8.3, now you will need to know a little bit more than just those facts. Okay, so there are some laws that is associated with the log functions. They're closely related to the exponential law that what we know from before. So the first law of logs is called the product law. So the product law of logs is, it says the following: when you have an expression's law, log with the base a, when you have a x times a y, that should equal to, you can break this as long as they are the product between x and y. You can break that into two logs with the additions. So it's the same base log a with the x plus the log with the same base a and a y. Okay, so these two, you can either add them or you can put that under the same log a but as a product, x times the y. Okay, so for example, if I have an expressions log 2 16 plus the log 2 32, from what we know from the previous sections, I know that if I change the 16 into the base of 2, so I can get into a log 2 2 4, and that, from the fact that we know this expressions is equal to 4. Okay, log a to the x, you get the x. Okay, and plus, if a log 2 with the same base as the first term, but with the 32, so change the 32 in the base of 2, so I know that this is equivalent to log 2 to the power of 5. So that expression is because these two are the same, so I know that this is going to be equal to 5. So the final answer is going to be equal to 9. Okay, so let's just verify about the law to see whether this is true or not. So if we combine these two terms under log 2, okay, but multiply the 16 with the 32, okay, as the x times the y. When you multiply that, you get 512. And 512 is equivalent to 2 to the power of 9. So when you convert that into a log 2, 2 to the 9, your answer is going to be equal to 9, which is the same as what we have here. Okay, so this is a good example to verify the law that is going to work. Okay, now the second law is called the quotients law of log. Similar idea, when you have the log a with the base a, but the terms that right after is a fraction, x over y. With that, you can break this into two parts with the same base as a log a x and a log a y, but is the subtraction. So you have a log a x minus the log a y. Okay, similar example, if you have a log 2 64 minus a log 2 8, I can easily turn the 64 into the same base as a 2, so this is going to give you a log 2 2 to the power of 6, and a log 2 8, you can turn this into a log 2 2 to the power of 3. And according to the facts that we know, the first term, I know that this is going to be equal to 6, and the other one is going to be equal to 3, so the answer is going to be equal to 3. Now, let's combine this, if this is true according to our quotient law, that a log with the base 2, when you divide the 64 with the 8, and you know that this is going to give you the log 2 8, and the log 2 8 rewritten in the base of 2, so you get a log 2 2 to the power of 3. Okay, and that is going to be equal to 3. So again, we know that this works for the quotients law. Okay, And then there's one more law here. It's called the power law of the log. And this power law is, in fact, is very useful. And it happens all the time that when you get an expression such as a log a x to the power of r, and that exponents r, in fact, can be put outside as a multiplier, as a r times the log ax. Okay, so this can be rewritten by bringing the exponents in front of the log as a multiply the entire log ax. Okay, so for example, I have an example here to show you that when you have a log 5, a cube root of 25. Okay, I know that square root of 25 is 5, but cube root of 25, that is the same as a 25 to the power of 1/3. Okay, a cube root is just the same in the exponential form is to the exponents of 1/3. So in that case here, what I can tell you is that if you know about this law, then right away you can bring this 1/3, okay, like over here. You can bring this 1/3 over to the other side, like in front of the log as a multiplier. So 1/3 times the log 5, 25, okay? Or if you look at this one here, I just want to show you how this is equivalent is by changing the base of 25 into a 5, because I have a 5 here. So 25 can go as a 5 to the power of 2, okay, to replace that 25 here. And then because of that, then I will end it up with a log 5, okay, and then I have a 5 to the exponents of 2 over 3, okay. And so because of the fact that we know log 5 to the exponents of 2 over 3 is equal to 2 over 3 from the fact that we know from before. But if this law here is true, then when I bring the exponents 1/3 in front of the log 5, 25, again, I'm going to have this as a 5 to the exponents of 2 to replace that 25. So that is the same as a 1/3 times this expression is going to be equal to 2. So again, I'm going to get 2 over 3, which is the same as well, okay? So this one is also the same. So that makes this law here is a good law to follow, okay? Now, I just want to show you guys one more thing about the technique that when we are solving exponential equations, but now this time I have to show you the method that using the log methods, okay? I just want to show you in the past, whenever we are trying to solve for the exponents, when we get something like 2 to the power of x equal to 8, we're trying to solve this by using the same base. Okay? Like this example is possible because the 8 can turn into the same base as the left side, which is the 2. So 8 is the same as a 2 to the power of 3. So when they both sides, the left and the right side has the same base, then we can say that the exponents must be the same. So x must be equal to 3, right? However, sometimes when you get questioned that you cannot have the other side turn into the same base. So in this particular example, 2 to the power of x equal to 10. And we know that for fact that we cannot change the 10 into the base of 2. So what are we going to do? Well, then I'm going to take the log on both sides. So I'm going to multiply log with the 2 to the x, so I get a log 2x. And I'm going to multiply the log with the 10 here, so I get a log 10. Okay? Now, both of this now, when you multiply the log to both sides, the base is going to be the 10, but you don't see it here because when you multiply the log, that means that you are using the log with the base 10. Okay, so basically, because of the power law, I know that log 2x is the same as when you bring the exponents down, okay, to in front of the log. So you have x times the log 2. Well, here you got nothing, so still a log 10. Solving for x, that means you divided both sides by log 2. So log 10 over log 2 is going to be equal for the x. Okay, so this is all in the base of 10. And because when we try to multiply the log on both sides, we are using the log with the base 10. Okay, so this will give you the exact form, log 10 divided by log 2, using your calculator. When you do that, you will get approximate values of a 3.32. Okay, so this is the example that I want to show you. So in fact, for any given exponential equation such as a b to the x equal to a, to solve for that x, that x is always equal to, well, in the log form is a log ba equal to x, right? But when you're solving for the x, like according to this example, that basically all you have to do is take the log 10 divided by the log 2, and that's how you're going to solve for the exponent. So when I have a b to the x equal to a, then x must be equal to log a divided by the log b. And this form is what we call the exact form. Okay. Usually we want you to leave the final answer in exact form, unless we ask for approximate form, and then you're going to use your calculator to calculate that in decimal. Okay, so this is going to be in approximate form, but this is going to be in exact form with the base 10.